Good morning, everybody. My name is Petr Holub. I'm from BBMRI-ERC, which is Biomedical and Biomedical Resources European Research Infrastructure Consortium. And I was invited here to talk about our view of how the infrastructures can actually stimulate the data sharing and help with issues related to it. And for me, it was sort of first close call to the e-trace platform. So I was a little bit shooting blind, but it actually turns out that we're after very similar issues that we're trying to solve. So is this supposed to work? What is BBMRI-ERC? We're basically a European entity which currently aggregates about more than 600 biobanks across the whole Europe, with more than 1,300 collections and an estimate of more than 100 million samples available. This was established in 2013 after a pretty long preparatory period and some also period of lack of funding, some bridging funding. And we're trying to harmonize the way biobanks are operating to deliver high quality biological material and data for different research projects. And as was mentioned already here today, this is the infrastructure. So we're aiming at supporting projects. When we do our own research as infrastructure, it should be on things that are sort of orthogonal to our users, in a sense that we can do the research on improving the quality of biological material, on provenance of the data generated and so forth. But typically the infrastructure itself is not doing the medical research, it's the users and the projects that are doing it or should be doing it. What the biobanks are about, it's a collective entity of biological material, data, expertise, and additional services such as analytical services, data curation services, and so forth, or hosting of the biological material and hosting of the data. Just to give you an example of the use cases, the users that we have is a prostate cancer project, for instance, which was aiming at improving the currently available screening based on prostate-specific antigen, which is far from optimum. Wrong people get screened, 2 out of 3 diagnoses are incorrect, and what is even more important, the most aggressive cancer types are actually missed. 30 to 40% of them are missed, and this has tremendous impact on the healthcare costs, of course, and not to mention also the societal impact. So the biobanks in Sweden got together to collaborate with the research group led by the groups in Sweden got together with Professor Granberg, and they set up a new study with the aim to develop new biomarkers based on the existing combinations of existing biomarkers, and with primary goal to identify the most aggressive cancers at early stage and demonstrate a clear impact to the economy. So it's called, the result is called STHLM3 model, which is coming from the Stockholm County name. And they have combined about 250 genetic markers and clinical data, and the outcome is pretty staggering. They got about 100,050 randomly invited people to the study. Many of them accepted. I mean, there was about 20% drop-off in the invitation here. About 11,000 men were recruited as a training data, and then about 110 1,000 people agreed to participate, and the results of the model is reduced number of biopsies by 32%, reduced number, which is even more important, number of benign biopsies is by 44%, and about 5 times improvement in identification of those aggressive cancers. And the results propagated both into publications as well as into products in collaboration with Thermo Scientific and Life Technologies. So these are, this is an example how you can use the biobanks that are collecting both the data and the biological material. And we as BBMRI-ERC look into this as a sort of continuum of material from the biological material to the data. And we're trying to ensure findability, accessibility, interoperability of it. More importantly, as we have discussed today, it's not only about having open data. I mean, if the open data is meaningless, if it's wrong, it doesn't make any sense to share it. I think in Spanish, I'm not sure if it's allowed to say it here in Catalonia, but in Spanish the saying goes, basura entra, basura sale, garbage in, garbage out. So it doesn't make sense to share garbage. We need, and this goes even deeper than the data, because if you have biological material you use to generate the data, and this material is garbage, you can use perfect analytical techniques and the resulting data is still meaningless. So this is why we see the continuum of the material from the biological material to the data quite important. And we're primarily focusing on human biological material and human data, so privacy and trust is absolutely critical. The main pillars of BBMRI-ERC is the IT infrastructure, privacy, respecting findability and accessibility. We are working on both community standards as well as the international standards, for instance within ISO TC 276. And we're trying to support the biobanks to actually use these and to also deploy open source software tools. We're developing, as a part of our common service IT, we're developing something called Biobanks, which is biobank in a box toolset based entirely on open source software. Transmart is somewhere in the pipeline to be also integrated. We have started with the tools that are the most critical for the biobanks, such as biobank information management systems and phenotyping information software. And then we're also moving ahead with integrating the analytical tools. LC, which means ethical, legal, and societal issues, which includes also stakeholder involvement, again dealing with the human material. And maybe one important distinction to what we have heard here so far is that we're aiming at many different projects, supporting many different projects. So we're not that much interested in having some data pulled into the consortium which runs some project, but we need to keep the data available for different consortia that come in and apply for the material and for the data from the infrastructure. And of course, quality part, which is both contributing to the standard development as well as helping the biobanks to actually adopt those standards in practice. And incentives and performance measurements are an important part of this workflow, because without them, even the biobanks, some biobanks might have issues sharing and demonstrating success of sharing, and of course collaboration and synchronization with other infrastructures such as ECRIN or Elixir or others. So from our perspective, we have the citizen, the patient, or the research participant in the center. They donate the data and the biological material to the biobanks. Some data actually also come from the healthcare registries into the biobanks, and there it gets integrated. It doesn't get pulled into one huge source in a sense that it stays within the biobanks. As we have seen on the map, we have quite a few throughout Europe. And then The researchers can ask to access request the access to the material, and then the results of the research get to the industry and then back to the patients typically. And as BBMRI, we're basically interested in the left part of this diagram up to supporting the researcher doing, for instance, the analytical data analytics or sample analytics for them. So what is available via BBMRI-ERC? It's the solid samples as well as fluid samples. It's RNA, DNA, cell lines, and in some biobanks also isolated pathogen, which is quite important for some security-oriented research. And in terms of data, there is a lot of data that come in directly to the biobanks as a part of either clinical process or as a part of the registries that are collecting the data. But nowadays we can see also new sources of data trying to integrate themselves with the biobanks, such as environmental data. There are now big ongoing projects around this, and it makes a lot of sense from the research perspective. However, it also brings in substantial issues in the data protection, because if you want to explore exposure of the people to environmental effects, you need to know where the people are. And you might have noticed that when you do the data privacy enhancement techniques, the location of the people and their birth, not dates, but even birth years, are significant sources of how you can revert the data protection, or how you can revert the privacy enhancement techniques and try to attack those things. And there are also biobanks working with non-human biological material within BBMRI context, but it's for the human medicine purposes. As I have mentioned, the core of the BBMRI business is the privacy-sensitive data, and I think David is actually going to talk a bit more about it in the next session. We have to care about privacy protection, and it's a continuum from the identifying data with no privacy protection at all the way to perfectly anonymized data that is completely useless. Unfortunately, there is always a trade-off between the value of the data and the privacy protection. Even if you use the best techniques that are currently available, such as epsilon differential privacy, for instance, there is a general consensus among the computer science community that you can't have both perfectly protected data and useful data at the same time. So it's usually a mixture of technical means, how you do the protection of the data, and organizational means, and also we would like to look in the future into additional legal protection of the people who are participating in research, because accidental identification of the people as a part of the research is inevitable, and we should be able to somehow protect them on top of all the previous measures. That if people are if their privacy is accidentally violated, they still should be entitled to, for instance, health insurance or travel insurance. I mean, we know about cases in the UK where a professor published a lot of data about himself on purpose, just to explore the limits of data sharing, and now he's unable to get travel insurance and commercial health insurance. So these are things that need to be looked into. And we're also trying to coordinate the code of conduct development for the upcoming GDPR for use of health data in medical research, because this is this will be another critical period next year when the legislation change, the GDPR gets enforced, and there are many things that still need to be clarified. Even the simple stupid pseudonymization, for instance, which is or the coding, as we may call it. the problem is that the requirements for this are not unambiguously stated in the GDPR, or even the process is not stated. So it is up to the domain-specific application, like the code of conduct for the GDPR, to actually develop the standards for this and promote those standards. So that people know what the pseudonymization, what type of pseudonymization they're actually expected to apply in practice when they have some practical project. I mean, for instance, one of the dangers is that the pseudonymization might mean, under very strict interpretation of the GDPR, which hopefully will not happen, but it might actually entail the same requirements as on anonymization if you don't, if you remove the mapping between the pseudonymized and the direct identifying data, the requirements of the resulting data set can be as strict as on the anonymized data set. And in the GDPR sense, that means, for instance, resilience to the attribute disclosure. So it's not about only identity disclosure of the people, but it's even about inferring attributes about people, which is much stricter requirement, and one needs to be very careful about it. But on the other hand, the code of conduct gives us an ability to actually define it for the domain, run it through the data protection authorities, the European Data Protection Board and the Commission, and get it as a, community standard, which turns into a soft law when applied under GDPR Article 40. I'll skip a little bit here because I think that these might be less relevant for you, just to give you an idea of the types of biobanks that we're working with. Clinical biobanks that are typically a fork in the clinical process, so that part of the material that's collected from the patients that have consented to participating in research is actually diverted to the biobanks together with the clinical data. On the contrary, population biobanks are typical large-scale biobanks that are trying to capture a good sample of the population so that they can be used for different public health screening projects. And the population biobanks are typically more systematically defined in terms of the data that they're collecting, while the clinical biobanks are more organic, in a sense, depending on what type of the treatment process the patient undergoes. This type of data ends in the clinical biobank too. These are on, say, two extremes of the spectrum. There are, of course, biobanks that are based on clinical trials, so these are part of the clinical process, but are much more strictly organized. And if you look into the types of the data that you can find in those biobanks, it's information on the biological samples, survey data, imaging data, medical records, of course, and access to the genealogical and national registries records, and of course physiological and biochemical measurements. Now, an important part that has been mentioned here a couple of times already is quality. Why do we need to care about the sample and data quality? I think that this has been already mentioned here a few times, and probably more yesterday. There are meta-studies, for instance, the one published by Friedman in PLOS Biology, showing that between 50% and 90% of medical research is not reproducible. And we need to do something about it. And the sources of that irreproducibility are ranging from the analytical processes, from the undefined reference material use, all the way to the study design, for instance. So what is data quality for us? It's the complete provenance information available from the source person to the biological sample, to the data generated, or to the data collected directly from that person. And what do we need is to have an interoperable provenance information. This is particularly important because we need to understand how the material was collected, how the data was generated. If the data, for instance, the data that was collected directly, was it measured or was it self-asserted? Was it collected through questionnaires or was it a measurement? has quite profound impact on the accuracy of what has been collected. If the donor donates biological material, it typically gets transported somewhere, processed, and stored. And depending on the type of the analysis, there are different requirements on how the material needs to be stored. And this should be described as a part of the provenance information. So you should have basically the provenance information on the data level and on the sample level, and these should be interlinked. And as a side effect, they can be, if privacy regulations allow that, it can be also used for dealing with incidental findings or for withdrawal of the informed consent, which is another important part of the infrastructure. If you're curating the data, the medical data or personal health data in the long run, there are people who want to withdraw their consent, and you should be able to propagate this wish into the dataset and remove them from the datasets where they can be identified either directly or as pseudonymized data items. So the provenance information needs to capture all these steps, needs to interlink back, ideally all the way up to the donor. And this link needs to be done in a privacy-preserving mode. And we need to be able also to distribute the provenance information across different stakeholders, so that the part of the provenance information can be stored in the clinical facility, part of the provenance information in biobank, and maybe the part which is about the data processing can be stored at EMBL, EBI, or somewhere where the final data set is stored, if it's distributed outside of the biobank. We have so far filed a proposal for standardizing this type of provenance information as a part of the ISO Technical Committee 276 on biotechnology in our Group 5 on data integration, because we believe that this first needs substantial work forward. There are already provenance information standards coming from computer science that are pretty generic, capable of capturing more or less any type of provenance information, but their application to the medical domain is not defined. There are ontologies missing, how to describe those processing steps, transportation steps of the material, storage information. So all this needs to be consolidated and put into a standard that makes the provenance information interoperable. The access procedures for infrastructure as ours are usually a bit complicated because we're typically dealing with the participant that donates the data together with the informed consent. You store it as coded, pseudonymized, or as directly identifying data, depending if the data is stored, for instance, in the medical facility. The original data is stored in the medical facility. It can be even directly identifying. And then you need a researcher that generates the project, undergoes ethical evaluation, and then only when the project is compatible with the informed consent, they can access the repositories of the biological data and biological material and the data. Alternatively, if it's not compatible, the biobank can actually apply for secondary use of the data within their own ethical committee, and if it's approved, it can be used. By the way, another important thing we're looking into is we're a federated infrastructure, and many biobanks or national nodes of BBMRI-ERC are acting on behalf of the researcher, trying to help them to do the data processing. And we're looking into how to scale up their computational facilities in a privacy-respecting manner, which is again quite a new field because there are, if you go into the cloud computing domain, for instance, there are not many widely accepted standards that would allow you to say, I want to use this computational service provider, computational capacity provider to process privacy sensitive data, to ingest those computational resources into my biobank and scale up my cluster of, I don't know, 50 machines into 5,000 machines for half a year because I have a large-scale project. And this type of this type of requirements that are legally necessary to allow the scientists to scale up their computations is again subject to a lot of development in the last year or two. You could have seen projects that are doing data processing on Amazon Cloud, but they are very specific in a sense that these are, for instance, ICGC datasets that have informed consent to do the data processing almost anywhere in the world. They have only requirement that the data needs to be put back into the US legislation once the processing is done. But they are quite specific. But if you want to use those computational capacities or storage capacities for generic human health data for research purposes, it's much more complicated scenario. So this is the access procedure written in another form. Our tools like the directory of BBMRI-ERC allowing to identify the resources of potential interest, then negotiating with them using the negotiator is how we're implementing the access to the resources. Typically, when you access the resources, you need to sign a DTA or MTA, material transfer agreement, or data transfer agreement, depending whether you're accessing material, physical material, or just the data. And then you receive the samples, and at the end of your research, you should report back to the infrastructure about the achieved research results, so that we can also include it in our own performance indicators. So the biobanks, just to conclude and provide a little bit of outlook, the biobanks are very rich resources, and compared to other types of data sources that you can find in the bioinformatics world, they might be a little bit more hard to access, but on the other hand, you can get to very valuable data to do the analysis. And BBMRI-ERC is trying to facilitate these type of projects by ensuring the visibility of the biobanks, promoting interoperability and quality of the data, and simplifying the negotiation access procedures. So that's it from my end, and I would like to thank you for your attention.
Peter, hi, it's Kees van Bokko from the Hive.
Yeah.
You said something, there's consensus in computer science that you can't achieve both encryption, pseudonymization, and useful data. But how about polymorphic encryption?
None of those seem to be. I mean, it's always about how resilient it is against the attacks. So what I was saying is you can't achieve perfect protection of the data resilient to any type of access while still maintaining useful data.
Okay. Yeah, but certainly, today we have ways to do this a lot better than.
Of course, and I would say that those differential privacy techniques are probably on the top spot at the moment, because they at least give you mathematical guarantees on resilience against different types of attacks.
Thanks.
And from this perspective, I would say that it's really always a combination of the technical measures, organizational measures. So typically as a part of the MTA or DTA that you sign with the user, with the requester of the samples or the data, you typically require them not to attempt any re-identification of people. So this is something that they become liable for when they receive the access to the data. And then, as I said, as the last resort, it would be also nice in the future to provide some add-on legal protection of the people. But even now, we have a lot of tools that we can work with. It's only to fight against the common dichotomy that you have, like here you have the pseudonymized data, and here you have the anonymized data, and that's it. No, it's not that.